Before we go into examples involving multiplying and dividing algebraic fractions, I might just go over some background theory first. And let's consider the first point. If we have a fraction where the numerator involves a product and the denominator involves a product, so let's say a times b over c times d, we can break the fraction up into a product of two fractions. In fact, these are equivalent statements. So the a multiplied by b can be broken up as individual fractions, a over c multiplied by b over d. Now, multiplication is commutative, which means that the a and the b can be swapped around. It doesn't matter which order you multiply the numbers in, the end result's still the same. So a over c times b over d is exactly the same as b over c times a over d, or at least in terms of the end result, or the value of the product of these two fractions. So we can use this to great effect for simplifying or manipulating fractions with multiplication and division. And the other little bit of theory that we need to go over again is that if you're dividing by a fraction, okay, you turn the division into a multiplication and you take the reciprocal of the second fraction. So, for example, a over b divided by c over d just turns into the statement a over b multiplied by d on c. So the c and the d just, you just sort of flip them around. Okay, so it's inverted. Why is this? In fact, I couldn't help myself. I have to go over this quickly with you, and I think it's really good to see. A over b divided by c over d is really just a fraction divided by another fraction, but expressed again in fraction form. So think of it as a one big fraction where the numerator is a fraction, okay, just a smaller fraction, and the denominator is another smaller fraction. When I say smaller, it's the denominator is itself a fraction. But this is not an ideal situation. So we don't want a fraction where it's a fraction where there's fractions inside fractions. So what we're going to do is we're going to multiply the numerator and the denominator by a product of both of the individual denominators involved. So this denominator here, this b and this d, okay, if you multiply a over b times bd and c over d times bd, okay, as long as you're multiplying top and bottom by the same thing, you're not changing the value of the fraction, but you're going to change the form of it, which is really cool. So doing that, if you multiply a on b times bd, you multiply the numerators, the numerator a times bd, so you end up with a bd over b all over bcd over d. Now we can cancel the b's and we can cancel the d's. Okay, that's why I've sort of crossed them out. So that cancels with that, and this d cancels with this d there. So we end up with AD, okay, over BC. So this AD, okay, over BC. Okay, and AD is really the same as A times D over B times C. And as we've seen before, this can be broken up into a product of two fractions. So the A over B can be split off as a separate fraction multiplied by D over C. And that's exactly what we have here. Okay, so this statement is exactly the same as what we've just stated earlier. All right, let's have a look at some examples. Okay, so there's 5 examples there. So, and they're fairly simple examples, but again, just to demonstrate the idea of the principle. 5x over 4 multiplied by 3x on 10. Now, we can swap the numerators around if we want to, but I think it's easier to just cancel diagonally, since the 4 and the 10 can be interchanged. So we could have this as 5x over 10. I think it's good for you to see this. So swapping the 4 and the 10 around, we have 5x on 10 multiplied by 3x over 4. Now 5 on 10 is just x on 2. Multiplied by 3x over 4, and then you just multiply numerators and then multiply denominators separately. So x times 3x is 3x squared over 2 times 4, which is 8. Now we could have saved a step by just observing that the 5 and the 10 can be reduced to 1 over 2. Okay, so if if you want to do that, that's fine. If you can see that, that's great. So we could just cancel out the 5 and turn the 10 into a 2, and that would also work. Okay, and it would save a step. Let's look at part B. So 2 over a times 3a squared over 8. We can see the same thing happening here. The 2 and the 8 can be reduced down to the equivalent fraction 1 over 4. So that becomes a 1, and this becomes a 4. Now we have a squared, which is just a times a. Okay, so in fact, that would disappear with that a there. You cancel, and you end up with a 1 in its place, since a squared over a, I might just write this down, a squared over a is really just the same as equivalent to a over 1, assuming a is not equal to 0, of course. That would be pretty silly. But these are equivalent, assuming a is not 0. So, all right. So just continuing on then, so you have 1 over 1, which is just 1, which doesn't do anything apart from leaving it as it is, okay, and we end up with 3a over 4. All right, part C, this is using the principle that we looked at, where if you have a division, just turn the division into a multiplication and invert the second fraction. So this will be 6 over x multiplied by 5 over y, and there's not much we could really do there, so that's just 30 over xy. Okay. Part D, same thing. We can just invert the second fraction, turn the division into a multiplication. Okay. Sometimes, if you're struggling to see the whole division, especially when we're involving indices, what you could do, if you want, you could do it like this: x squared is just x times xy over 3. Okay, multiplied by y over 6x. All right. This only works for very small indices. If it's x to the power of 20, you're not going to write 20 x's, right? So this is just more for you to see the cancellation occurring. So one of the x's from the top will cancel with this x here. Okay, and I don't think there's much else we could do, and just multiply across. So we end up with xy over 18. All right, last one. So 5 over 2x plus 6 multiplied by 4x minus 10 on 15. All right, two things we can do. We can factorize this numerator here, the first fraction, and factorize the numerator of the second fraction. We can also see that we can cancel diagonally or reduce diagonally 5 over 15. Why don't we do that first? So we could reduce this to 1 over 3, and we can factorize this denominator and this numerator. Okay. So we can take out 2, x plus 3, multiplied by, now 4x minus 10, we can again take out 2, and that's going to be x minus 5 over 3, and these 2's will cancel as well. So it will be, we can cancel diagonally, so 1 over x plus 3 multiplied by x minus 5 on 3, and we can just multiply across now. So numerators being multiplied across, that's a 5, sorry, x minus 5 over x plus 3 times 3, so that's going to be 3x plus 9.